A very good afternoon to all the students. So in the previous two sessions we have gone through the brief discussion on this Advanced Encryption Standard algorithm, and in today's class also we will just continue with the same topic of Advanced Encryption Standard. We will just rush through the PPTs, and at the point where we need to explain this key expansion, we will have some detailed discussion on it, and then we will simply go through the slides, right? So this is how I have planned for today's session. So coming to advanced, we will go with the history and when this AES has been implemented. Any idea? We have gone through this discussion. In what year the AES algorithm has been implemented? In the year 2001, right? So after that we will see transformations that are used in the AES and the key expansion. This is what we are going to concentrate in today's session, and after this we will quickly go through the AES cipher examples and the analysis of AES, right? So coming to the introduction part of this AES, as I told that this AES is abbreviated as Advanced Encryption Standard, and it is a symmetric key cipher and it is a block cipher which is published by National Institute of Standards and Technology in the year 2001. Right? See, this is a simple history of this AES, and we know why this AES has been implemented. Can anybody tell me what is the reason why this AES has been implemented? Anybody please respond. Why this AES has been implemented?
Since the DES become somewhat unsafeable in the present era, sir.
Right. So DES, if you take the data encryption standard, this is unsafe in the present era. That means it is attackable, or this is vulnerable to brute force attack, and it is also vulnerable to differential cryptanalysis, and it is vulnerable to linear cryptanalysis. So this is all because of the key size that we have with the DES. The DES will have 56-bit key size. So it is unable to resist this BFA, DCA and LCA attacks. So for this reason we have gone through the triple DES where the key size is about 118 bit. Though it is the TDS is able to resist this BFA, DCA and LCA, the disadvantage with this TDS is it has complex computations, right? It takes a lot of time to compute this TDS algorithm. So to reduce the complexity of the computations, where we can reduce the number of rounds or whatever operation that are involved inside the TDS can be re-implemented or it can be modified, so that the main purpose, the main objective of this AES algorithm is to reduce the computations that are taking place inside this TDS. As I told that this AES is 6 times faster than the TDS. It's not DES, it is TDES, and it is more efficient than the TDS algorithm. So for this purpose the AES algorithm has been invented. It is also known as residual algorithm, as we told that it takes the plain text in terms of blocks, and each block is consisting of 128 bits. So 128 bits of plain text is converted into 128 bits of cipher blocks. So 128 bit we take it as a single block. This is the plain text, and you apply this AES algorithm which results in generating a 128 bit block of the cipher text, right? And the key size that are used in this AES is 128 or 192 or 256. So the key size that is used is dependent on the number of rounds that is used in the AES algorithm. So if we take the AES with 10 rounds, we should use the key size as 128, and if we take the AES as 12, we take the key size as 192 bits. And if the number of rounds in the AES algorithm is taken as 14, then the key size should be 256 bits, right? So I told you that we can also call this as AES 128 version, and the second version you can call it as AES 192, and the last one we can call it as AES 256. So these are the three versions that are available in the AES, right? And the criteria defined by the NIST for selecting the AES fall into three categories. One is the security, how far this AES algorithm is able to resist the threats. That is, what are the threats we have discussed? That is the brute force attack, and the second one is differential cryptanalysis, and the third one is linear cryptanalysis. How far this AES is going to resist all these attacks, and how far it is providing the security from these attacks, this is one criteria on which the NIST has selected this AES algorithm. And the second one is the cost. So you can implement the AES algorithm either by using a software or by using the hardware also. So this can be implemented using the software or hardware. And the cost incurred in developing this AES algorithm is less than the TDS or DES which we have discussed in the earlier sessions. And coming to the implementation part also, why the cost is being less means, as I told that this AES can be implemented with either the hardware or software. And when you implement it by using the hardware, you can use the cheapest microprocessors, then also it will work fine, right? AES will work even with the cheapest microprocessors or less memories. Because of this particular reason, the cost of implementing this AES is very much less than compared to that of the DES algorithm. So is it clear the criteria on which the AES has been developed?
Yes, sir.
Right. And coming to the number of rounds, this particular DES, TDS and AES, all these makes use of either the fistal ciphers or the non-fistal ciphers, right? So DES makes use of the fistal cipher, where each and every round is implemented with fistal blocks, which may consist of the S boxes, P boxes, XOR operations or swap operations, any kind of combination you can put it in the fistal boxes, right? In the similar fashion, the AES is a non-fistal cipher that encrypts and decrypts a data block of 128 bits. This we all know, right? And the number of rounds in DES is, how many rounds will be taken by this DES algorithm?
16, sir.
16, sir.
16 rounds, super. And the number of rounds by which we can implement this AES algorithm is, it can go to 10, 12 or 14. And as we discussed in the earlier also, the key size depends on the number of rounds we are going to implement this AES. The first one is, if we take the 10 rounds, it is going to take 128 bits, and if it is 12 rounds, we are going to take 192 bits, and if it is 14 rounds, we are going to take 256 bits, right? And this is the block diagram of the Aes encryption cipher, right? So the Aes decryption cipher is something different, where we will make use of different algorithm, right? Aes algorithm will make use of the Aes algorithm only, but we are going to use different components in the deciphering technique, right, or in the decryption technique. So if we make use of for example, round key, then in the round key in the encryption, then we are going to use the inverse round key in the decryption. So we are just making use of the inverse characteristics of each and every component for the decryption, Right, so this is the general block diagram of the AES encryption cipher. As we know that it is going to take the input as 128-bit plain text, and the first and foremost step that is going to happen in AES is the pre-round transformation. So here what it will do, it will take the 128 bits of key which is represented as K0 and which can be given as 4 words, which is W0, W1, W2 and W3. So here we are going to apply this XOR operation of this K0 with this pre-round with that 128 bit plain text. So it will be generating some output, and as I told that the intermediate results are always stored inside an array called state array. State array is a 4x4 matrix where each cell consists of 1 byte, right? So after this, after getting the output and storing it in the state array, this state array is given as input to round 1. In this round 1, we will have different operations. What are the 4 steps involved in round 1? Any idea? Can anybody please tell me what are the 4 rounds involved in this round? What are the 4 steps?
First one, substitution, sir.
Substitution bytes. Super. What is the second step?
Shift rows, sir.
Super. Shift rows. And what is the third step?
Mix columns.
Mix columns. And step 4 is round key, right? So each and every round starting from round 1 to round n-1, all these 4 steps will be implemented except for the nth round. So nth round, what is the step we are missing in the nth round?
Mixing columns.
Mixing columns will be eliminated, right? This is for purpose, and this is how we are going to take, right? So each and every round it will accept the key of size 128 bits, which is again represented as 4 words, right, like this, and finally we will get this 128 bit cipher text, block of cipher text. So this is how the AES algorithm is going to work, and this is where we have to stress more, right? So we will give the cipher key which is of size 128 bit or 192 or 256. As I told that we will be concentrating on the AES with 10 rounds. So let us fix ourselves that the key size is around 128, right? 128 bits. Why? Because we are taking only 10 rounds of AES. So we are giving the input to the AES algorithm as a 128 bit cipher key. 128 bit means we can make use of, or we can divide it into 4 words, right? But actually we require n+1 keys. That is, if n is the number of rounds, we require a total of n+1 sub keys. So if we take the AES consisting of 10 rounds, we will take the n value as 10, and additionally we need to have 1 key regarding this pre-round transformation. Therefore 11 sub keys are required, and each sub key is of 128 bit, right? So how we are going to convert this 4 words of key into, totally we have 44 words, right? So we need to convert 4 words of key to 44 words of key. That is how we do it, by making use of the key expansion method, right? We are going to expand the 4 words of key to 44 words of key. This is one important topic which we are going to discuss in the next coming slides, right? So we need to know how this AES is going to handle the data, right? So in DES, as you know that it is going to take 64-bit blocks, and it is going to convert these 64-bit blocks into 64-bit cipher text. But in AES, when we are discussing in the previous sessions, I might have told that this AES always concentrates and operates based on the bytes or words, right? This is very important. So whatever operation you perform in the AES, it is going to take it in terms of bytes and words only, right? We know what is a byte. 1 byte is equal to how many bits?
8 bits, sir.
1 word is equal to, super, 1 word is equal to how many bits?
4 bytes, sir.
4 bytes, right? 4 means how many?
32 bits. 32
Right,
bits.
32 bits, right? So this B0, listen here, this byte is represented with small lowercase b. So B0, B1, B2, B3 and so on up to B7. Therefore this represents how much? So B0 is 1 byte, B1 is another byte, B2 is another byte. So if we combine 8 bits, we need to represent it like this. As I told that you need to make use of the column measure order, right? When you are storing the data and when you are dealing with this AES algorithm, you are not going to store it in the row measure order, you are going to make it with the column measure order. Clear? Right.
Yes, sir.
Column measure order means you need to represent it in the form of columns. So one word, as I told that it is equivalent to 4 bytes. So represented by B0, B1, B2 and B3, and word is represented with lowercase w. And as I told that you always make use of a column measure order. So this is the way you need to store, right? So one block is equal to how many bits? One block in AES is equal to how many bits? 128 bits.
128 bits.
That is equal to 16 bytes, right? That is equal to 4 words. So this particular representation is very important. One block is equal to 128 bits or 16 bytes or 4 words. So this 16 bytes of data is represented like this, right? So this is one word W0, and this is another word W1, and this is another word W2, and this is another word W3. And when you are going to store this particular block of data, as I told that you should always make use of the row measure order, right? So we are going to store it as B0, B1, B2, B3 and B4, B5, B6, B7, like this. This is what is called as column measure order. Right. So always make it habituated that while you are dealing with the AES, you always deal with the words, and everything should be written in the column measure order. And what is this one? This is called as the state array. Again I told that the state array is again a 4 by 4 matrix, and this represents 0th byte of 0th word, first byte of 0th word, second byte of 0th word, like that. This is how we are going to represent, and every column is represented as a word. This is one word, and this is another word, and this is word 2, and this is word 3. So is it clear? This is what we have discussed in the first class of AES regarding the representations of data in the AES. Right? Clear?
Yes, sir.
Right. So this is what we have told. Block to state and state to block. How we are going to transform a block of data to a state array, and how we are going to transform the state array into a block of data. As we know that the block is nothing but a 16 byte data. So B0, B1, B2 and so on up to B15. We have 16 byte data. and we need to represent or we need to store it inside the state array in the form of words, right? So this is how you are going to map. S00 is nothing but byte 0, S10 is nothing but byte 1, right? It is nothing but a column measure order. In the previous slide also I have told that we need to write in the column measure order like this, right?
Yes, sir.
So after writing this, the first byte is represented as S00, which is nothing but 0th byte of 0th word. So this is word 0, am I right or not? And this is word 1, and this entire column is word 2, and this entire column is word 3. So S00 means 0th word, 0th byte of 0th word. So this is B0. And this one represents first byte of 0th word. So 0th byte first word is B1, and this represents second byte of 0th word. Therefore this is nothing but byte 2. For example, if I consider this S23, that is nothing but second byte of word 3, right? So it is nothing but B14. This is how we are going to do it. So when we want to convert, this is how we are going to convert this block to state, right? And there is a necessity that you always convert the state to byte also. So that we will do it in this fashion, right? So you start with the first element, that is S00, and you go downward direction, and then you again move to the top element of the next column, and you go in the downward direction, again go to the top element, go in this direction. This is how you need to follow, right? Here he has given, the other has given this direction, right? So is it clear up to this point?
Yes, sir.
Yes, sir. Clear, sir.
Yes, sir.
So here is an example of how we are going to convert the plain text to a state, right? So we are going to take a plain text like AES uses a matrix, right? This is a text which is called as AES uses matrix without any spaces, right? So how many letters are there in this one? AES uses matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14, right? But an AES algorithm always requires how many bytes of data? It requires 128 bit, right? It requires 128 bit or 16 byte. So if you take each and every character occupies 1 byte of data, so here I have only 14 bytes. So the remaining 2 bytes has to be padded. So ZZ, here I am padding it, the block. You know the concept of padding, right? Padding is nothing but adding the dummy data to the block in order to complete the entire block. So originally this AES algorithm requires 16 bytes of data, but I have only 14 bytes of data. So I need to fill the remaining 2 bytes of data with a dummy data. So that is where I am filling it with dummy data ZZ. Is it clear up to this point?
Yes, sir.
Right. And you need to make use of the hexadecimal notation, right? Everywhere you will make use of the hexadecimal notation, where you have the digits starting from 0, 1, 2 and so on, A, B, C, D, E and F. You all know very well about this, right? So how can I represent this hexadecimal notation 0? Every hexadecimal notation is represented with 4 bits. So this is 0, 0, this is 0, 0, 0, 1. What about A? What is the binary notation of hexadecimal A? A is nothing but 10, right? So 10 means it becomes 10, 10. Right. Right. So now let us take that A, these alphabets are given the numbers. So A has a number of 0, 0, and B is having the second number, right? So it is having 0 1, C is having 0 2, D is having 0 3, and E is having 0 4. Like that, Z will be having some number, right, which is a dummy number, right? So here you can take that A is represented with 0 0, E is represented with 0 4, S is the 13th letter, therefore I get it as 12, U as 14, here S as 12 again, E as 4. Like that I have represented with the hexadecimal notation like this. Clear? Is it clear? Any doubt regarding this? So you might have got the doubt that why this Z is 19. Actually there are 26 alphabets, therefore if we start A with 0 0, Z should be 25. Am I right or not?
Yes, sir.
But why it is represented as 19 means you convert this 26 into hexadecimal notation. So 26 divided by 16. So it goes one time, therefore it is 16, and the remainder is 25, right? It's not 26, and the remainder is 19. Therefore I get this as 19 hexadecimal notation. Clear?
Yes, sir.
Yes, sir. It's clear, sir.
Yes, sir.
So I have 16 bytes of data, and this is the block of data, and this is B0, this becomes B1, byte 1, this is byte 2, and this is byte 3. Like that I have byte 15. So in order to convert this block of data into state array, so how is that you have to write? You have to write it in the column measure order. Therefore 0 0, and after that I have 4, this one, and after that I have 12 like this, and 14 like this, and this is next word. So I start it with the new column. So 12 is this one, 4, again 12, and again 0. So like that we need to convert the given data block into state array. Clear?
Yes, sir.
Right.
Yes, sir.
So this is what we have discussed in the earlier session also. Structure of each round at the encryption site. This is where we are going to discuss with respect to the encryption only, right? So we have 4 different steps. The first one is, as you told, that it is substitution bytes, and the second one is the shift rows, and the third one is mix columns, and the fourth one is add round key, right? So what is this box which is having the checks like this, black and white checks? It is nothing but the state array. As you are going to store the intermediary results in the state arrays, every step will have an output, and that output has to be stored inside the state array, and that state array becomes the input to the second round. So the output of substitution bytes is stored in state array, and that becomes the input to the shift rows. Again, the output of shift rows is stored inside the state array, and that becomes the input to the third step, that is mix columns. So this input, the output of mix array, again stored in state array, that becomes the input to the fourth step. And the output which I get from this add round key is stored inside the state array. So here is the importance of state array. Every intermediate result that you generate in the AES will be stored inside the state arrays. Clear?
Yes, sir.
And this mix columns is going to be mixed in the last round. And the next topic is the Aes transformations, right? What are the transformations that I am using? What are the 4 steps we have here? Substitution bytes, it is nothing but substitution, right? And shift rows, it is nothing but permutations. And the third one is mix columns, which I can call it as mixing. And the last one is XOR addition, which I am calling it as round key. So these are the 4 transformations, I'm going to take it inside this AES algorithm, right? The first one is substitution. These are nothing but the 4 steps involved in each and every round of the AES. First one is substitution, second one is permutation, third one is mixing, and the fourth one is XOR operation of the key, which we can call it as round key or key adding. Anything is okay, right? Clear? And coming to AES substitution, AES like DES makes use of a substitution. So it makes use of an S box. Very important, right? You should know the difference between the S boxes used in the AES and the DES. What is the size of the S box used in DES?
6/4.
Super, it is 6/4. And what is the size of S box used in AES? It is 16/16, right? So that is the only difference we have in this S box. Very important difference, right? Because of this only we are able to achieve the required properties of the AES, and we are able to achieve better ciphers than that of the DES, right? So AES uses 2 invertible transformations, that is substitution bytes. The first transformation, substitution bytes, is used at the encryption side. To substitute a byte, we interpret the byte as 2 hexadecimal digits. This I told in the earlier class, right? Everything you store it inside the state array or the block as a hexadecimal notation. For example, if I take the hexadecimal notation 73, right? So this is taken as the first 4 bits of the byte. This entire thing is 1 byte, right? Let us represent it with B0. The first 4 bits is nothing but the 7. This represents the row. And the second 4 bits represents the column. Clear? So in the S box of 16/16, I have to find out the value which is present at the junction of this 7th row and 3rd column. So whatever value I get, I have to substitute this 73 with that value. Let us assume that it is AE, just an assumption, right? So in the 7th row and the 3rd column of the S box in the AES, the value is AE. So what I have to do is I have to substitute this 73 with AE. This has to be repeated for each and every byte inside the state array. Is it clear? So how many times I have to apply this substitution? How many times? It is nothing but how many bytes are there in the state array? How many bytes are there in the state array? B0, B1, B2, B3, 16. Therefore, this is an example where I have taken this B0 as 73 and I got the value as AE. So how many times I have to apply? I have to apply this for all the 16 bytes. So 16 independent transformations, byte to byte transformations will happen in this AES substitution. Clear?
Yes, sir. It's clear, sir.
Right. So here I take a block in the state array. This is the state array. So I take a block and the first bytes, first 4 bits, A of 16, right? This one is considered to be the row number, and the next 4 bits, that is B of 16, will be taken as the column. So whatever intersection value I am getting, I am just replacing it. So AB is replaced with CD. So I just put this CD inside this same state. Clear?
Sir.
So this is the table where this AES algorithm is going to use for the substitution bytes, substitute bytes transformation table. So how many columns are there? You can see here, starting from 0 to F, which are nothing but 16 columns. So how many rows should be there?
7, sir.
No, S box of AES is What is the size of S box?
16 by 16, sir.
16 by
16 by 16, right? So there should be 16 columns. I am just making a part of it, right? So this is the 16 by 16 S box. Clear?
Yes, sir.
So this is the substitution transformation table which we are going to use at the encryption side only. So what is that we are going to do in the decryption side means we are going to use inverse substitution bytes. That is a different table where this substitution bytes transformation table and inverse substitution bytes transformation table are inverses to each other, right? So this is the inverse substitution bytes transformation table which we will make use of it in the decryption side. It is also a 16 column and it is also a 16 row. That means it is a 16 by 16 matrix. Clear? So you should know the difference between the substitution bytes table and inverse substitution bytes. So we are all discussing about the encryption side only. So what is that we are going to do in the decryption side means we are going to use the inverses of this thing. So they have defined everything which is the everything, right? Each and every step will have the inverse, right? So the inverse substitute bytes transformation table is going to be used inside the decryption side. Clear?
Sir.
Right. So this is an example of how we are going to convert this one state matrix into another state matrix, substitute bytes. So if you look at this one 0 0, I'll just look at this few examples, one or two examples. 0 0 means the first 4 bits represent the column number, row number, and the second 4 bits represent the column number. So 0th row, 0th column. What should I substitute? I will go for this substitute bytes. So 0th row and 0th column. What is the value?
63, sir.
63.
63, sir.
So I substitute this 0 0 with 63, right? So let us take another example. Let us go with 14 or 19. Let us go with 19, right? So it represents first row and ninth column. Am I right or not? So let us go with the first row and ninth column. So this is first row, and what is the ninth column? I have the combination, I will have it as D4. So I replace this 19 with D4. So this is at the encryption end. So if I want to convert this state into substitute bytes at the decryption end, I should not use the substitute byte transformation table. I should go for another S table which is inverse substitute byte transformation table, right? So let us see what happens this F2, right? If you look at this F2, you have to go for the F row and second column. You have to go for inverse substitution bytes. So what is F row here? This one. Second one is 0 1 2, this one. So the combination is 0 4. So if I make use of this one, I will get it as 0 4. Clear?
Yes, sir.
Yes,
So
sir.
this is at the decryption end, right? And what is the second step we have after substitution?
Permutation.
Permutation, which we are going to implement in this AES with the help of shift rows technique, right? So another transformation found in a round is shifting, which is shifting of bits, which we also call it as the permutation of bytes. Here we are not going to make use of bits, right? Remember always that AES is going to make use of the concept of bytes or words, never bits, right? So shift rows means in the first row we take the state array, again we will take the state array and we are going to shift it. How we are going to shift means we are going to shift towards its left, right? And this is at the encryption side. And what happens in the decryption side? Any idea? If you are making use of shift left in the encryption, what is that we have to use in the decryption side?
Shift right, sir.
Super, shift right, right. But there is a technique where we have to stick to these particular rules, that the first row which we are taking in the state array, there will not be any shift. But for the first row, we have to shift 1 byte. And second row, 2 byte shift has to be happen. And in third row, 3 byte shift has to be happen. This is how we need to make use of these rules, right? First row, 1 byte shift, 2 rows, 2 byte shift, 3 rows, 3 byte shift. And if it is at the encryption end, you have to shift it towards its left. And if it is at the decryption side, you have to shift it towards its right. Clear? Right. So at the decryption side, the transformation is called as inverse shift rows, where we are going to shift it towards the right hand side. Simple reverse right. So this is how we are going to take it. So if you take the example of state array like this, 63, C9, FE and 30. This is first row. So for the first row, how many shift operations you have to perform? How many bytes?
1, sir.
No, okay, you are getting confused, right? So this is the 0th row. Let me take like this. 0th row, how many shifts? How many byte shifts? No shifts. Therefore, you can observe here that the same thing happens here. 63, 63, C9, FE and like that, right? And this is the first row. First row means how many shifts?
1 shift, sir.
1 shift. So F2 is shifted towards its left hand side and it is kept like this. So it will move like this, F2 and then 63 and then 26. See here. F2, 63, 26, and the F2 which you have moved towards its left will go towards its right hand side. That's it. And now if you consider the second row, how many shifts you have to perform? 2 byte shift, not bit shift, 2 byte left shift. So these 2 bytes are shifted towards its left hand side. Therefore the first one is 70, D4, C9, 9. And the third row, 3 byte shift. So this entire block will move towards its left hand side. So D4 comes first and then FA 63 and 82. So reverse is nothing but we have to make a right byte shift, right? The rules applies the same. Row 0, 0 shifts. Row 1, 1 shift. Row 2, 2 shifts. Row 3, 3 shifts. Clear?
Yes, sir.
Right. And what is the third step?
Mixing, sir.
Mixing, right? So we are going to take the state array and we are going to take one word of each and every state array and we are going to multiply it with a constant matrix, right? So the constant matrix is given here, this one. This is for encryption. 2 3 1 1 1 2 3 1 1 1 2 3 and 3 1 1 2. This is for encryption. And the inverse mix column is also there. This is also a constant matrix which has to be taken while you are decrypting it, right? Which is 0E, 0B, 0D, 09, like that. This is constant, right? We cannot change it. This is already defined by the inventors, right? So what you will do is you will just mix it. What you are doing, you take this state array, one word has to be taken. This is W1, right? What is this one? W0, this is W2 and this is W3. So one word will take it and you multiply it with the constant matrix, right? So what is the constant matrix size? It is 4 by 4. Am I right or not? Here you can see this is a 4 by 4 matrix, and similarly inverse mix column is also a 4 by 4 matrix. So you take the 4 by 4 matrix. What is the size here? What is the size of each word? Which is nothing but 4 by 1. We have 4 rows and 1 column. So the resultant will be also a 4 by 1 matrix, which we can treat it as a word, and you just replace this word with entire word with the new word. That's it. Clear?
Yes, sir.
Right. So let us postpone this AES mixing with polynomial. That means mixing operation can also be done by making use of the polynomials also, right? So let us postpone this topic of polynomials addition and multiplication. It's a very simple topic, but we are simply missing the remaining topics. So we'll just skip it, and if time permits, we'll discuss it in the next session, right? And what about the inverse mixed columns? Inverse mixed column is a transformation that is basically which is same as the mixed column transformation only, but we are going to use the inverse mixed column matrix for the decryption. Clear?
Yes, sir.
What is the last round we have? What is the last step in each and every round?
Adding keys.
Adding round key, right? So addition of round key is nothing but whatever state matrix you get from the output of mixed columns, you have to perform an XOR operation with the round key, right? So the round key is nothing but again a 4 word, again a 128 bit or a 16 byte, anything you can call, right? So a round key is a 128 bit key, or it is a 16 byte matrix, or it is a 4 by 4 matrix, or you can take it as 4 words matrix. Anything is you can take it, right? And what is that you are going to do in this add round key is you are taking one word of the state matrix and you are going to perform the XOR operation of one word of the key. This is what we are going to do. It's a simple XOR operation, nothing more than that, right? So add round key adds a round key word with each state column matrix. The operation in the add round key is nothing but a matrix addition, right? See here. So this is one state matrix. We are taking one word, this one, and this is the key, one word of the key, right? So let us assume that the key is K0 or K1. So every key will have 4 words, W0, W1, W2 and W4, like this. So we'll take the W1 of K1 and we'll take W1 of state matrix 1 and we'll perform an XOR operation. Simple thing. And whatever result you get, you just put it inside the state matrix of the output as word 1. And in the similar manner, you take W2 from this state matrix and you take W2 from the key matrix. You perform the XOR operation, whatever result you will get, you just store it in W2. That's it. Like that, you have to apply it for each and every word. That is a simple technique which is called as add round key, right? So what is the output you will get? The output is again a 4 by 4 state matrix, and this state matrix should be given as input to the next round, right? Clear?
Yes, sir.
Right. So in the next session we will discuss this AES key expansion, which requires almost half an hour of time. So we are quickly going through this AES ciphers, right? So AES is nothing but it is going to use 4 types of transformation in both the encryption as well as the decryption. We saw it, right? Just now we have seen. What are the 4 types of transformations? Substitution, permutation, mixing and adding, right? That is at the encryption side. And what about the decryption? It is nothing but inverse substitution, inverse permutation, inverse mixing and inverse adding of the key, right? We don't have inverse, I think. we will just have the adding of round keys only. We will see what happens, right? So in this standard, the encryption algorithm is referred to as the cipher, and the decryption algorithm is referred to as the inverse cipher, right? So if you look at the original design of this AES, ciphers and inverse ciphers of the original design. So the plain text is a 128 bit. This is an encryption side. This is on encryption side. Sending. This is a 128 bit key, and which is given to the first round, which is called a pre-round calculation. So in this we are taking the key K0, which is having the word numbers as W0, W1, W2 and W3, and we are just performing the XOR operation here. And after this, the output is given to round 1. So substitute bytes, shift rows, mix columns. You can observe the wording that is used in the encryption side. So substitute bytes, shift rows, mix columns, add round key. These are the terminology that is used at the encryption end. And at the round key, add round key, I am using another key K1, right, which has the words starting from W4 through W7, right? And again the output of this round 1 is given to round 2, again the output of round 2 is given to round 3, and similarly the output of round 8 is given as the input to round 9. And in the final step of adding round key, you can observe here that it is K10, right, key 10, which consists of the words as W6 to W36 to W39. Clear? And final round, you can observe here that the mix columns is not present here, but every other step is there. Substitute bytes is there, shift rows is there, add round key is there, everything is there. And in the final round also, we will give the key 11, where it has W40 to W43. So totally we have 44 bytes of key. Clear? So after the ciphertext of size 128 bit is transferred from the sender to the receiver, this is what we have to observe here, right? So it is, we are doing it in the reverse order. If you observe, so the add round key, which is a preliminary step, is done at the first round, where the keys are given. Observe here, initially the add round key is taking W0 to W3, but here the add round key at the decryption end is taking W40 to 43, right? So and in the round 1, what is that they are doing? Inverse shift rows and inverse substitute bytes, and similarly inverse column, mix columns and add round key, right? So this is somewhat confusing at the decryption end. If you observe that these two, that means the substitute bytes and shift rows, are inverses to each other. So that is the reason why, let me clear it. See here. So the invertibility of substitute bytes and shift rows combinations. So shift bytes and shift rows are invertible. So if you give the inverse of this substitute bytes and shift rows, we will get in this manner: inverse substitute bytes and inverse shift rows, right? And finally this one, the mix columns and the round key are inverses to each other. So this is at the encryption side and this is at the decryption side. So if you inverse these things, we will get like this, right? So inverse shift rows we will get here, and after that inverse substitute bytes, and then add round key is given as the third step, right? And inverse mix column is given as the fourth step, right? So this is how we are going to decrypt the things at the AESN, right? So this is one implementation. The other implementation is you can directly make use of the reverse of this, right? So add round key followed by inverse, and this is inverse, and this is inverse, and this is also invert add round key. But here we are not going to use this W36 to W39. We are going to make use of W4 to W7, like that. So there are two implementations, anything is okay, right? So this is a confusion decryption part where the author is trying to say that the substitute bytes and shift rows are inverses to each other. Therefore, you can just reverse it like this. Clear? See here, this is what the author is giving. So if you inverse the substitute bytes and shift rows, I will get this inverse substitute bytes and inverse shift rows. And here this, if you inverse this mix columns and add round key, I will get inverse mix columns and inverse round key like this. Clear? Any doubt regarding this one? So like that, every round it will perform, and finally the receiver will get a 128-bit plain text. Right. So this is all about the AES ciphers and reverse cipher. Reverse cipher is nothing but the text that you get after applying the encryption technique or encryption algorithm, and inverse cipher is the text which you get after applying the decryption algorithm. So in simple terms, you can simply say that the encryption is called as the cipher and the decryption is called as the reverse cipher. Right? Clear?
Sir.
Right. We'll see this example in the next session. And coming to AES properties, when we are discussing the DES properties, we have seen two terminology, right? One is the avalanche effect and another one is completeness. What do you mean by avalanche effect? Even a single bit change in the plain text will affect lot of bits in the ciphertext, right? That is what is called as avalanche effect. So let us check what happens in the AES algorithm. What is the effect of this avalanche effect in this AES, right? So let us change only one bit in the plain text and compare the results, right? For example, if you look at this example, there are two plain texts, right? So how many bits are differing between this plain text? Everything remains same except the last bit, right? So there is only one bit of change between these two plain texts. But if you compare the ciphertext of the plain text 1, ciphertext 1, you got the ciphertext like this: 63 2C D4 5E like that. And the ciphertext 2 that is obtained from encryption of plain text 2 is something very different from the ciphertext 1, right? So it is 63, it is 26, 2C F3 DF 9B like that. So for a single bit of change in the plain text, you can observe that there is a complete change of ciphertext that is generated by the AES. So that is what is called as avalanche effect, right? So a single bit of change in the plain text will make a lot of bits changes in the ciphertext. It will affect many bits in the ciphertext. That is called as the avalanche effect. What is the need for this avalanche effect? It is a property that describes the strength of any encryption algorithm. One bit change results in many bit changes in the ciphertext, means that is something related to the diffusion and confusion, right? So we need to have a lot of confusion and diffusion. Clear?
Yes, sir.
So this is a cipher key which I have taken all zeros, but then it is able to generate a effective ciphertext from the plain text. So what is this cipher key all zeros means? It is nothing but a weak key. We have seen the weakness of the DES algorithm, where the major weakness is based on this keys only, weak keys, right? Though you have taken the cipher key as all zeros, you are able to generate an effective ciphertext with the given plain text, right? This is another strength we have. And coming to the Aes analysis, as I told that the entire AES has been developed based on 3 criteria. One is the security, second one is the implementation, and the third one is simplicity and cost. Coming to Aes security, as I told that the AES was designed after the DES. So the DES is in 1977 and the AES is in 2001. So all the attacks that were known up to this 2000 year are clearly addressed in this AES, right? So the brute force attack, the AES is able to resist this brute force attack, so it is definitely more secure than DES due to larger key size, right? So what is the key size of DES? It is 2 power 56 key space, sorry. And what is the key space of this AES algorithm? What is the key space of AES algorithm? It is 2 power 128, right? So we have a huge key space where the attacker cannot easily get the key by making use of this brute force attack. So we can definitely say that the AES is more secure than the DES because of its larger key size. And coming to the differential and linear cryptanalysis attacks, there are no differential and linear cryptanalysis crypt attacks that are done on the AES by this time, right? So at the present era also there are no differential and linear attacks that has happened on AES. That is the strength of AES. This all happened because of the key space that we have with the AES, which is nothing but 2 power 128, right? And statistical attacks, numerous tests have failed to do statistical analysis of the ciphertext. Even though you get the ciphertext from the AES algorithm, it is impossible, it is highly impossible to again reconstruct the plain text or again to get the key from the ciphertext. It is almost impossible, right? So all the statistical attacks have failed on the AES who tried to get the ciphertext or who tried to make the statistical analysis on the ciphertext, right? And coming to AES implementation, as I told that AES can be implemented either by hardware or software or firmware also, right? So the implementation of software is by making use of the tables, and the hardware is by making use of some processors or some memory units. Like that you can make use of or you can implement the AES in the hardware also, right? If you want to implement the AES using software, you can make use of the tables or functions or any algebraic structures or matrices. Algebraic structures means nothing but matrices, right? So you can make use of them and you can implement it in the software also, nothing wrong in it. And coming to the simplicity and cost, as I told that the algorithms used in the AES are so simple and they can be easily implemented using cheap processors and minimum amount of memory, right? So in any way or in any angle, the AES algorithm is superior than the DES and the TDES also, right? So that is the reason why the AES is most familiar algorithm with respect to the block and symmetric key ciphers, right? So in today's session we have quickly gone through the AES algorithm. We have gone through the history of AES algorithm, and we have seen how the AES algorithm is implemented and what is the block structure of each and every round, what are the transformations that are used in the AES algorithm. And similarly we have gone through the block diagram of entire AES design, and then we have gone through the criteria which is required for implementing the AES, such as the cost and implementation, how we can implement, and what are the security, what is the security that it is going to provide. All these things we have seen in the today's session, right? So that's all for today's session. Thank you one and all for joining the session.